Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to cover the topic of visible light spectrum. Okay? And before I do, I wanted to let everybody know that I have published 5 Kindle books, and if you want to read any of them, you let me know in the comments below, and I'll send you a link to the latest one. You can read all 5 if you like, and you let me know what you think of them. Alright, enough advertising on my YouTube video. Let's continue on. In order to comprehend all the language of the visible light spectrum, I have to teach you some technical terms. Let's start with a wave. Okay? Now, if you have ever taken a surfboard out to an ocean or wherever, a large body of water where you find a lot of waves, and you have ever surfed with a surfboard, this is going to look pretty familiar to you. Those are waves. Okay? So imagine that you are at an ocean with a surfboard and you are surfing on the waves. This will help you understand this a lot better. Okay? Now, the wave starts at a certain point. The crest of the wave, which would be right here or right here, you can see it here or here, okay? The crest of the wave is the top of the wave. When the wave crashes on the beach, it reaches the trough or bottom of the wave, like this here or this here. Now, do you guys remember when I popped up a video entitled Pappas Book 7 Proposition number 238? Well, if you'd have learned that, you would have understood parabolas, because what you're seeing here is one parabola after the next. Isn't that what you're seeing right there? That's exactly what you're seeing. And you would have immediately recognized that as I did that. Okay? So, if you did not learn from Pappas Book 7 Proposition number 238, I'd like for you to go over there, learn from that, then come back. Okay. So let's just assume that you have actually done this, and let's go on with this presentation. What about the frequency of waves? Well, you know that waves crash onto the shore. Now, when the wave crashes onto the shore, that's a point. Okay? So, at this point, what you would do is you'd count the number of waves that crash on the beach during a specific period of time. You could say, okay, 4 waves just crashed on the beach in 1 minute. So if you say 4 waves crashed on the beach in just 1 minute, and it's continuing to do this, you could say, well, for every minute that passes, we're getting 4 more new ocean waves. Okay? And that's how you'd measure frequency. But what about wavelength? Okay? This is where you would get your yardstick. Okay, get your yardstick, you go out there, and you find 2 waves. Okay? Wave number 1, wave number 2. Now you put the first end of the yardstick, I'm going to draw it with a line. If I can grab hold of this. Okay. What you're going to do is you're going to draw a line. You're going to start from right here, and this will be the beginning of your yardstick. And then you draw that line. I know it's kind of sloppy, but there you go. And hopefully the other end of the yardstick would touch this wave. Now, if the waves are closer together, obviously it's going to touch like the middle of the stick rather than the very end of it. But between this point and this point, that would be your wavelength. That's what the wavelength is. Okay? Really simple terminology, don't you think? And radio waves work the same way. So you're already getting a lesson about radio waves just as much as you're getting a lesson about light rays. It's the same type of effect. Alright. Our eyes can only see certain colors. That's because these colors belong to what is called the visible light spectrum. Okay, our eyes can only see certain kinds of light. You can't see other light that's outside the visible light spectrum. Okay, that's why it's called a visible light spectrum. We can detect wavelengths between 400 nanometers. Now, nanometers are really, really tiny. So you got 400 nanometers, and this is called the violet light spectrum, and 700 nanometers, which is called the red light spectrum. Okay? The other colors we see are between the 400 nanometer and the 700 nanometer light spectrum lengths. Okay. Why is all this important? Because solar panels can absorb a certain part of the light spectrum. That means that when the light actually hits the solar panel, it is not absorbing or harnessing enough of the light spectrum to generate all the electricity that you would want. So, in a future video, I'm going to discuss how to overcome something like this. And what we're going to talk about, what we're going to actually discuss, is something called an axially graded index lens. If you have one of these axially graded index lenses, you can overcome this limitation. In the meantime, I hope you check out the description box of this video. I have left a link to a web article that discusses the visible light spectrum. I didn't just leave one link, I left two, so you can go and check those out. Alright, I will tell you more in a future video, so I'd like for you to stay tuned.